morning, guys, and welcome to the yet another lecture of simulation of business system. And today is lecture 4. Actually, I have wrongfully written it as lecture 3. It is lecture 4, and we are trying to understand the basic concepts or premises of how do we simulate business systems. And if you look at the learning agenda, we have already covered the nature of simulation. We have also looked into the brief history, how the simulation has already originated. So, these were covered as part of the lecture 1. Then systems, models and simulation, we covered it as part of lecture 2. Okay. Then what are the definitions associated with this, what are the major applications and real world applications, that aspects of it we also covered. And then why do we need to do simulation, this question also we answered. All these were part of lecture 2. Then how do we build simulation model, we covered in the previous lecture, and what are the main aspects of simulation, especially on things like various aspects of discrete versus continuous simulation. And similarly, we also did with static versus dynamic simulation, and we also studied deterministic versus stochastic simulation. Deterministic versus stochastic simulation. And then we also discussed from here why we are going to focus more towards next event simulation. And we also talked about what we call as the timing mechanism, and we understood the concept of what we call it as simulation time. Okay. This much aspects we covered in the previous lecture, and now today what we will try to do is we will take so this was our lecture 3, and now we are going to get into a simple example. We want to see a simple simulation system and see how the principles that we have studied so far gets accumulated into single concept and see how it actually works. So, today we will be focusing more towards developing this simulation using a pen and paper model, pen and paper approach to understand basics of this approach. Okay. So, let us see how we can do this today, and then we will go to the then we will see. So, before we do the simulation, I want to run again through the major components of discrete event simulation model. As I mentioned earlier, this is discrete. Discrete means, in a simple sense, discrete implies countable events at instantaneous points of time. Remember, we talked about the people coming into a banking system or a simple queuing system, and today we will actually look into similar example like that. Okay. So, we are talking about a discrete system, and the trick with the simulation is every simulation model or each simulation model has to be customized to the target system. So, the most important thing that you need to realize is there is no single model that fits all. So, it is all dependent on the target system. Okay. So, it is dependent on target system. So, whatever be the system that you want to model, depending upon that you build customized simulation model. Okay. So, this customization is the place where it actually, this is why it is called as a time consuming process. So, that is why people say simulation is time consuming, purely because you have to customize it to the target system. And there are several components that to exist. So, and these components are common, but they have to be customized to a particular need. So, the first one is what we are going to call it as a system state. Okay. System state is one of the aspect. We already talked about what is the state of the system. and this is in a very simple way, it is a variables, or another way a collection of variables, that describe state of what? State of the system. Okay. So, the collection of variables, a collection of them together that describes the state of the system is what we call as a system state. Then we talked about simulation clock or simulation time. So, the simulation clock means specifically what it does is it gives you the current value of the simulated time. So, if you remember, I have yesterday drawn a graph in which I tried to explain to you guys is that if you think about this as a time and this as number of people in the system in a queuing system, and we drew a graph like this for some point of time, then 2 people, then 1 nobody, then it goes up like this. So, you are more in the discrete simulation, you are more worried about these instantaneous points. Okay. You are not worried about what is happening in between. So, this area, the time in between where nothing happens in the system is ignored. So, your simulation time jumps from this time to this time to this time, then it jumps to this time, then from there it jumps to this, and like that. So, it is not the real time, it is actually the time. So, the main thing is in between times are ignored. You are not worried about these ones, these are ignored. You do not care about what is happening there, because the state of the system only changes at these discrete time points, which are demonstrated at one point. So, this kind of a time is called as a simulated time, and the simulation clock keep track of the simulated time. Then the third one is the event list. We already seen what an event list is, we know what is an event also. The event list is the times of future events as needed by the model, So, event list is mostly you can think about in the form of a calendar of events. Some people call it as calendar of events. So, what are the events that are going to happen in future and when are they going to happen? The event and its time, okay, the future events and its times put together in a tabular form or a list form or a calendar format is what we typically call as an event list. And as the simulation clock jumps from one event to another, the event gets pulled out of the event list and the new event gets updated. Okay. So, that is the event list. Then we talked about is the statistical counters, because we know that simulation, as I said earlier, is a numerical analysis. So, when you have a numerical analysis, you need statistical counters. So, what do? They to accumulate various quantities for output. So, if you think about the number in the system, so let us say x denotes the number in system, then what we do is we keep on doing as time progresses, x gets on x equal to, you get a summation of x, all x's, and when the simulation is over, you divide it by the time and then you kind of get a value of how many people per whatever time period. Okay. So, that is one way of looking into this. Okay. So, this accumulation on this is basically what we call as a statistical counter. Then the next one is also called as an initialization routine. Initialization routine means to initialize the simulation model to time equal to 0. or how do you start the simulation at the beginning of the time. This is not the actual time, this is the simulated time, okay, not the real time. So, how do you initialize a simulation model to time t equal to 0 and the simulation time is what we do in the initialization routine. Then comes the timing routine. The timing routine is, it is to determine next event time, okay, and type. What is the next event time and type? Whether it is an arrival, whether it is a service completion, whether it is a machine breakdown, you determine this and then advance simulation clock. Okay. So, you determine the time and the type of the next event, and then you advance the simulation clock, so that the next event actually happens. So, the timing routine ensures that the simulation model keeps on ticking as time progresses. Then comes the next one, what we call as event routines. And event routines, the job is to carry out the logic for each event. So, if you assume the event is an arrival, okay, so assume event equal to arrival, then what happens is a person arriving into the queue will check whether the server is free or server is busy. Okay. If the server is free, then it will immediately go to the server, get served, okay, get served. Otherwise, go to the queue. Okay. So, this logic, what happens when this particular thing happens, is taken care of by the event routine. So, how would each event, when it happens, what it should do next immediately is determined by the event routine. Then comes something called as a library routines. This is quite common and very well used. These are utility routines. And what does these routines do? Utility routines that generate random variates, pseudo events, etc. So, I said that we use random numbers or random variables or random variates to do the simulation. Why? Because the random variates are used for simulating uncertainty, or what we call as the stochastic part of the simulation model is done with the help of the random variates. So, the routine that generates the random variates, so that you can model uncertainty, is taken care as part of this particular library routine. Similarly, the pseudo events, the beginning of the simulation, end of the simulation, all those aspects are also taken care of by this approach. Then comes the report generator, and report generators, its job is to summarize and report results at the end of simulation. Okay. So, you summarize and report the results of the simulation summarize this at the end of the simulation. That is the main job of the report generator. And why do you need this? Because again, as I said, the simulation is a numerical analysis using a model, and this data is required to get estimates of the system performance. That gives you the estimates. So, this report is important for you to calculate these various estimates. Then comes finally the main program. What it does is, it ties all routines, subsystems together and ensure their execution in the right order. Okay. That is what happens with the main program. So, all these routines, all these kind of routines that we talked about, all of these guys are tied together by the main program, and then it ensures that they are executed in the correct order. So, this is how a complete simulation system works. So, you now know that the simulation software is not a simple software anymore. It is actually a complicated software with various subroutines and modules, submodels and other aspects, which are all taken care and working together with the help of a main program tied together, so that the logic of execution is important. And now, because it is a complex system, it is also very important to ensure that the model that you are building is the right model, and there is no logical flaw in this, because if you have a logical flaw, then your simulation output will also be in trouble. So, if you have a garbage model, then you will end up getting a garbage output. Okay. So, this is the GIGO principle, garbage in, garbage out. Okay. So, we want to avoid that. Okay. So, our aim is to avoid this. Okay. All right. So, now we will look into the next aspect of the simulation, and what we talk about it as the simulation entities. You have already heard me using this word entities. Okay. So, remember, there are events, there are routines, there are libraries, there are now entities, and entities are very important aspect of it, and by definition entities are those objects that compose the simulation model. Okay. The objects that together make the simulation model is what we call as the entities. What are they? Usually they include what? Customers, parts, paperwork like messages or information, okay, etc. May also include resources like servers or machines, etc. So, what we are talking about it is, these are the objects. So, when we talk about the single server model of a bank, the one of the entity is the customers that come into the system. Then also the paperwork, if they might be coming to fill the loan form or something, then that is also part of that, also you can think about as an entity. And also the server or the bank teller or the machines that are used in that process also includes as the object of the simulation. They are characterized by data values. Okay. So, entities are characterized by data values called, these data values are called attributes. So, when we say entity have attributes, when they say this, an entity have attributes implies data values that characterize that entity. So, that data values are called as the attributes. So, for each entity that is part of the simulation model, for each entity that is part of the simulation model, there is a record or a row in the list. Okay. So, for each entity that is part of the simulation model, whatever entities that is part of the simulation model, there is a record or there is a row, one row in the list. Okay. In the list of whatever, you can call it as the entity list, some people call it as the event list, okay. Some people call it as a calendar, whatever you want to say, whatever you want to call it, etc. In any one of those, you actually have a row, a particular record, a row is maintained for each entity that is part of the simulation model. Okay. The columns of such a row are the attributes of the entity, So, here like if you say that a customer 5 arrived, if this is a entity, then the attribute, so this will be the row of the entity, you will have a row on this, and one of them will be the arrival time, then you will have another called service start time, service end time, departure time. Let us say these are the attributes of this particular case. Then you can say that the customer 5 arrived, what is arrival time, when did the service begin, when did the service end, and when did the person left the system. So, these ones, okay, these becomes the attributes and this becomes the entity. Hopefully, now you understand the concept of entities in a simulation model, or when we talk about simulation entity, what they are. So, how do we model? Okay. Typically, what are the major modeling approaches in doing this? Okay. There is the first approach, the first and the most importantly used one is the event scheduling. Okay. So, what happens is, as described in the time advancement, okay. So, what did we describe in the time advancement? The time advancement, we actually said that determine the next event's time and type, and then advance the clock, advance the simulation clock. This is what we mentioned in the time advancement. So, the event scheduling is pretty much this, as described in the time advancement, determine the next event's time and type, and then advance the simulation clock. Okay. And this is usually coded in a general purpose programming language. Many a times you have a general purpose programming language that actually would implement this concept of event scheduling. Okay. C, C++, Python, people use different programming languages to do that. The second approach, the modeling approach, is what we call as the process, is where the focus is on entities and their experience. Okay. So, what we try to do it is the one approach is do the event scheduling, which is quite popular. The other one is follow the process approach, where you focus on the entities and their experience. Okay. And usually requires a special purpose simulation software. So, the softwares, if you are focusing on the entity and their experience, if you take the entity approach, then what you are going to have is you require a special purpose simulation software to really deal with that, like Simon, SimScript, all those kind of things are are part of such kind of an approach. Okay. Now, in the simple example that we were promising about the single server queuing model, we discussed earlier that we will be working on this and we will do a hand simulation of this, so that we can understand how the system works. So, a single server model, as I drew earlier, okay, it is like there is a server, one individual serving here, and there are entities waiting to get served, and there are people in the queue, they are all waiting to get served. And as when an entity comes in, when a new arrival happens, if the server is free, it will go directly or it will join the queue, depending upon the status of the server. So, before doing this, we have to make some assumptions. So, let us start with the first assumption, assume interarrival time. Okay. So, they are independent, interarrival timers are independent and are identically distributed. Okay. Typically, we call it as IID, identically and independent and identically distributed random variables. We will soon have a lecture on what we call as probability, which is specific to the simulation systems. But as of now, assume that all the inter-arrival times, the time between arrivals. So, there is one entity that is arrived right now, and here is another entity who has just arrived, second entity. This time in between them, what we call as inter-arrival times or time between arrivals, this time are identically and independent. So, the time for this, the T1, if you take this, or Ti, and let us take another arrival. Okay. This is another arrival, and let us take this as Tj. The Ti is independent of Tj, which means the value of Ti does not influence the value of Tj, neither the value of Tj does not influence the value of Ti. So, they are independent to each other. Okay. So, you might have studied in probability about independent events where the intersection is 0 and those kind of things. We will study that later, but assume that the independent means the occurrence of Ti has no influence on Tj or vice versa. So, all the times are independent, but they are identically distributed means they all follow the same probability distribution. Okay. We will see an example for the time being. Then again service times. Service times are also IID, okay, and are also independent of the inter-arrival times. So, we know that these are IIDs. The service times are also IID. Service times is the time spent by the server with the customer. So, this is what we call as a service time. Okay. The time spent by the server with the customer. They are also IID, independent, identical and independently distributed, but they are also independent to that of the inter-arrival. So, these T's does not have any influence on the S. So, the Ti, Tj do not influence Si, Sj. Let us say Si and Sj are the service times. Okay. Ti and Tj are the inter-arrival times. Okay. Queuing discipline. So, this is the way in which the next person is called from the queue. there are people waiting in the queue, whom will you call the next person? The main rule we are assuming here is FIFO. Okay. That stands for first in, first out, okay, or first come first serve. It is also called as FCFS, first come first serve, okay, but we call it as FIFO, first in first out. So, for assuming that whoever comes in the first gets served first. So, the people who come later will join the back of the queue. So, they will be kind of joining the back of the queue like this, all right. There are other queuing disciplines. The other disciplines are queue discipline are, one is called LIFO, which stands for last in, first out, okay, LIFO. Then there is another service called SIRO, service in random order, okay. Then there is HVF, LVF, there are quite a lot of queue disciplines, but there are many other disciplines. So, I just gave 2 examples of this, but for this we are looking at the FIFO is the queue discipline for this example, okay. You start the system empty, nobody is in the system and idle, okay, at the beginning of the simulation, beginning of the simulation, or what we call as time equal to 0. At time t equal to 0, the system is started empty and idle. So, there is nobody in the system and the server is idle. So, idle is the server, empty means no customer, okay. So, that is the initial starting condition of the system. Then when would the first customer arrive? Okay, we have to make that happen. So, first customer arrives after an inter arrival time not at t equal to 0. So, the simulation clock starts. So, if you think about it graphically, this is the time, this is 0 and here is the number of customer. So, the system will remain 0 for some time and after some point of time the arrival will happen. So, this is where the C1, the first customer will arrive and this is the number of people will be 1, 2, 3 like this, and this will continue for 1 until some point of time, and then maybe somebody else will also come, then it will become 2 and then the first person service got over, then it will come back to 1 and like this, okay. So, this is C1 and this is where the C2 will happen. So, this time, okay, this is the time is the inter-arrival time after t equal to 0. So, the first customer will arrive after the beginning of the simulation, okay. So, first customer will arrive some time later following inter-arrival times, okay, and not at time t equal to 0. Okay. So, when you go and open a bank, people will come in little later, that is what we are trying to simulate. Stopping rule, okay. Then how do we stop the simulation? We started the simulation, it is running, so how do we stop? Okay. Stopping rule is when the nth customer has completed arrival into the system, okay, then we stop. So, if you say n is equal to 5, which means after 5 arrivals, you can change this condition. You can say instead of this completed arrival, you can change this to change to completed service. Then that means 5 people have finished the service. So, as soon as 5 people join the system, so then here in this case you can see that you will have this is a C3, C4, okay, it comes down, goes up again, this is your C5, this means 5 people have arrived into the system. Okay. But if you say 5 people have complete service, this will continue further. Okay. So, depending upon what is the stopping condition that you are used, the simulation will run for different durations. Okay. So, the duration, the simulation duration, sorry, the simulation duration depends upon the stopping condition. Okay. So, that is what we will be doing in this model. Okay. Now, once you do the simulation, so what? After that what you do? The you have to do a lot of estimate of quantities and other aspects. So, one of them that you will end up estimating is the expected average delay in the queue, which means how long does the customer have to wait before getting served. How long will you end up waiting in the queue, okay, before you starting to get served, excluding the service time. So, you just focused only on the waiting time of n customers, how many ever customers completing their delays or completing their, this delay means waiting in queue. Delay implies waiting in the queue. So, how long does a customer have to wait on an average? Okay, that is what you are trying to find out here. Expected average number of customers in the queue. How long will be the average queue length? Okay. So, if you go to a, so it's like if you reach the system, how many will be waiting for you, will be waiting ahead of you. So, this is an important question. So, people decide when to go for service depending upon answering this question. Then the third one is expected utilization, or what we call as proportion of time busy of the server. Okay. So, it basically is, the question is how much of the time the server is busy serving the customer. Okay. So, if you say that the time, simulation time is for 100 minutes and the server was busy for 72 minutes, then it is 0.72 or 72% of the time the server is busy, and rest of the time the server is idle waiting, because there is nobody there to get the service. Then comes the other possible options. You have many other possible options. Those options include the maxima. So, this is the maximum of queue length, can be maximum waiting time, that kind of thing. Then minimum, so how quickly. Okay. Then time or number in the system, this is another example. What is the time in the system? Time in the system means time in the system is equal to time in queue plus time to be served. Okay. That is the time in the system. Number in the system, the number in the system is equal to, okay, number in the queue plus number that is served. Okay. So, that is the number in the system. So, time in system and the number in the system can be taken care of that. Then proportions. Proportions is the quartiles, what proportions of them, quantiles, and then variances. variance is how, what is the dispersion. So, these are all measures of dispersion. How much is the data varying in the system? That is also part of this analysis. Okay. And you should remember that we are talking about discrete time versus continuous time statistics. Discrete time is the like statistics of events that happens at specific time instances. So, like arrival. Okay. So, that is happens in the discrete time, whereas continuous time statistics, for example, is the time for which the server is busy. That is a continuous time statistic, because whenever it is busy, the server continues to remain busy. It is not an instantaneous thing. It actually happens when the customer is being served by the server. So, now with this much of basic preparation, what we will try to do is we will try to create a simple simulation model of a system where a single server, as we discussed, one server and people coming to get served and waiting in the queue. And also remember that in this model we are not talked about, and one aspect we should also remember here is nobody who comes to the system leaves without getting served. So, that means a person who coming in will come and join the queue. So, if we think about it, if this is the server S1 and it is serving an individual, and here is a queue, people are waiting in the queue, okay, and if a new person coming in, okay, he will join the queue, he will not leave. If you leave, this is called balking. Okay. You see the queue is long and then you leave. So, there is no balking, no renegading, no joking. Everybody who comes in comes to the queue, sits and waits properly as civilized individuals. With this, what we will now do is we will try to create a simulation model of the system as required, and then we will try to do a hand simulation for few number of entities, let us say 5 entities, and see how it works. Okay. Thank you.